Okay, so we covered black surfaces and how they behave and how you can calculate radiation heat transfer between them. Most surfaces aren't black, so we have to talk about real surfaces, and that makes things a little bit more complicated. So again, if I want to do a heat transfer problem, what I'm really interested in for every surface is the difference between how much radiation is emitted and how much is absorbed, because that will be the net radiation heat transfer from the surface. Both of these quantities get substantially more difficult to think about when your surface isn't black. So the absorbed radiation becomes more difficult because the radiation that's coming and hitting the surface can be stuff that was actually reflected off of other surfaces, and then actually all of that incident radiation isn't absorbed. Some of it might be reflected. So this part of it gets more complicated. We'll talk about this next time. But actually even the emitted part of it gets more complicated, and that's because a real surface is going to emit radiation at a rate that's less than a black surface. And actually a real surface will have emitted radiation that can be a pretty complicated function of wavelength and also direction. So direction for a surface is typically specified in terms of these spherical coordinates, right? So we have the first spherical coordinate being the angle measured from the normal, right? So that's basically what we call that theta. Theta equals 0 is straight up. Theta equals 90 degrees is sort of at a glancing angle. And then the second spherical coordinate is this rotating coordinate around the normal, right? So in general, you can have emitted radiation be a function of both the theta and this phi angle, right? So a function of direction as well as also a function of wavelength. And so things can get relatively complicated from that standpoint. So the way that we characterize how much radiation a surface emits is with this quantity called the emissivity. And it's just the ratio of how much radiation is emitted by a real surface compared to how much radiation is emitted by a black surface at the same temperature. Sometimes you'll see this called the emittance. It really basically means the same thing. It's a number that has to be between 0 and 1. Obviously, you can never emit more radiation than a black body, and you always, the smallest amount of radiation you can emit is 0, right? And if the radiation that's emitted is some complicated function of wavelength and direction, then in general, the emissivity must also be some function of wavelength and direction. So that's the most detailed version of emissivity is what's called spectral directional emissivity. And that is the emissivity that is a function of the direction and also the wavelength. So spectral means wavelength. So it's the ratio of the radiation emitted at a given direction and wavelength to the amount of radiation emitted by a black body at the same direction and wavelength, right? So we call that epsilon, and then it's a function of wavelength, lambda, and direction, theta and phi, right? So this is my spectral directional emissivity. It's emitted radiation per unit area, and then it's per unit wavelength, and it's per unit solid angle, right? So watts per meter squared per micron per what's called sterradians. So let's talk a little bit about what this means, because you probably haven't seen that before. Sterradian is a differential angle on a hemisphere like this, right? So if I was talking about a differential angle, like a differential theta or a differential phi, that would be, a differential angle that would have units of radians. If I'm talking about a differential theta and a differential phi, and the area, the differential area that it defines, that differential set of angles define on this hemisphere right here, that's a sterradian, right? That's a differential area that is defined by differential theta and differential phi, right? So steradian, that's what that means. So yeah, emitted radiation per area per wavelength per solid angle divided by the same thing for a black body, right? And obviously this has to be between 0 and 1. Rarely will you find information that's this detailed about a surface, right? Somebody must have then set up an instrument that actually measures at every wavelength and every direction what the emissivity is. Occasionally you'll find emissivity as a function of theta, because usually emissivity might depend on theta. It'll almost never depend on this phi angle or the rotation angle. It might depend on theta. So here's an example of directional emissivity. They're calling it beta here, but it's what we're calling theta, right? So theta equals 0. I have an emissivity that looks like it's about 0.95, and then as I go away from normal 0.95 until I get to about 60 degrees when it really starts to drop off, and when I'm down here at 80 or 90 degrees, my emissivity is approaching 0. So you can see pretty big variations in emissivity, in spectral directional emissivity as a function of theta. Like I said, almost never as a function of phi. And again, this is pretty detailed information, more detailed than you're typically going to get for a surface. So spectral directional emissivity is the most detailed information you can get about a surface. What's a little bit more typical is if you're given hemispherical emissivity. So this is the emissivity based on the emitted radiation integrated over all directions, right? So this is, you're basically going to take the emissivity and you're going to integrate it from, you're going to take the radiation that's emitted, you're going to integrate it over this entire hemisphere. So from theta equals 0 to 90 degrees and from phi equals 0 to 360 degrees. So you're going to get the total amount of radiation emitted over all of the different directions, right? So this is hemispherical emissivity, still a function of wavelength, right? It's emitted radiation per unit area per unit wavelength divided by the same thing for a black body. These are what we were calling spectral emissive power, right? So the denominator here is the black body spectral emissive power, right? This is what's given by Planck's law. And the numerator here is spectral emissive power of the surface, right? I've shown you this figure before where we have the spectral emissive power as a function of wavelength, and then Planck's law sort of establishes this upper limit, the biggest it can be, and then a real surface has to be underneath that, right? The real surface has to be below that. The hemispherical emissivity is just the ratio of these two quantities, and it is a function of wavelength, right? So here it looks like the hemispherical emissivity would be pretty low, and then as I move to higher and higher wavelengths, you can see that the spectral emissive power is approaching the black body spectral emissive power, so the emissivity, this hemispherical emissivity, is getting higher. So that's hemispherical emissivity. The last quantity we should talk about is what's called total hemispherical emissivity. Right, so here we're dealing with an emissivity that's based on the total amount of radiation integrated over all directions and over all wavelengths. Right, so I've integrated over the entire hemisphere, right, over the entire hemisphere, and I'm going to integrate over the entire spectrum. That's total hemispherical emissivity. So this is emitted radiation per area divided by the emitted radiation per area for a black body. This down here is the black body emissive power. This is just sigma t to the fourth, and then this is whatever I get when I integrate this curve over all wavelengths, right? So basically this top quantity is the integral of the actual spectral emissive power, and then this bottom is sigma t to the fourth. It's the integral of the black body spectral emissive power, right? That's what this equation here says. You can calculate the total hemispherical emissivity if you're given the hemispherical emissivity. So if you think about it, if this is my spectral, so my hemispherical emissivity, which is a function of wavelength, and it starts low and goes high, the total hemispherical emissivity isn't just some kind of average of this. You actually have to you actually have to know the temperature of the surface. So here's our equation for what the hemispherical emissivity is. Right, this is my spectral emissive power. My spectral emissive power is given by the product of the hemispherical emissivity and the black body spectral emissive power, right? So this guy right here is the black body spectral emissive power, and then this is my hemispherical emissivity. And I have to integrate that overall wavelength. So if you think about it, if the hemispherical emissivity was just 1, then this is 1, and I get on the top here sigma 2 to the 4th over sigma 2 to the 4th. That's just going to be 1, which makes perfect sense, right? If my hemispherical emissivity is 1, then my total hemispherical emissivity also has to be 1. But, if that's not 1, then what this is doing is it's weighting the black body emissive power according to this hemispherical emissivity. So if you think about it, then I can have this spectral emissivity, I can have this hemispherical emissivity, but depending on what the temperature of the surface is, this can give me different values of the total hemispherical emissivity, right? So let's imagine using this spectral emissivity, this hemispherical emissivity, for a very high temperature surface. If I have a very high temperature surface, then the black body emissive power is really high at lower wavelengths, right? So when I do this integral, these lower wavelength values are going to matter more than these higher wavelength values. I would expect the total hemispherical emissivity would be pretty low. And then as the temperature drops, well, now I'm going to get into a situation where these higher wavelength values are going to matter more, because the black body emissive power, the black body spectral emissive power here in this numerator is higher at higher wavelengths. So I'm going to shift from where the lower wavelength values matter to where the higher wavelength values matter, right? I'm going to shift from having a total hemispherical emissivity that's relatively low to having one that gets higher and higher and higher for this particular variation in the hemispherical emissivity. So the point being that the total hemispherical emissivity is a function of temperature, right? Even if the hemispherical emissivity is not, because it's weighted by the black body spectral emissive power. There are some values of total hemispherical emissivity available. You can get that pretty readily in various handbooks. It's also programmed in EASE. So let's go look at EASE. If you go to options, function information, you go to heat transfer, and you go down here to total hemispherical emissivity, you can see different surfaces. And if I click on one, you can see I have to tell it the surface and the temperature, and it'll tell me the total hemispherical emissivity. And you'll notice it's not just the material, it's also how the material was prepared, right? Was it polished? Is it smooth? You can sort of take from this that, how you handle a surface impacts a lot what the emissivity of that surface will be. So if I hold a surface with my greasy fingers, I'm going to, change the emissivity relative to if I'm really careful and always hold that surface with gloves or something. So these values are useful, but they're not, like a property in the same way that enthalpy or conductivity is, right? They depend kind of a lot on how the surface was handled. All right, let's go back here. So that's, everything from, if you go all the way to the one edge, we have this spectral directional emissivity. If I integrate that over all directions, then I get what's called the hemispherical emissivity. So now I'm only a function of wavelength. If I integrate over all wavelengths, I get total hemispherical emissivity, right? So now I'm only a function of temperature. When we deal with the problems that we're going to talk about in this class, we are going to make some assumptions about how these surfaces behave. And the first assumption is that the surfaces are diffuse. So we're only going to deal with surfaces here that have emissivity that doesn't depend on directions, right? So we can't deal with this surface characterized by the pink line. We'll only be able to deal with this surface characterized by the blue line, where the the spectral directional emissivity is a constant over all directions, right? Something bad happened here. Let me fix this. All right, there. So the other assumption that we'll make, at least for a little while, is that our surfaces are gray. And what gray means is that the emissivity doesn't depend on wavelength. So we can't deal with a hemispherical emissivity that looks like this, right? We can only deal with hemispherical emissivities that are constant across all wavelengths. So these are pretty limiting conditions. I think that this second one is a lot more limiting than the first one. What we will do towards the end of in a couple, 3 lectures is we'll extend our gray surface analysis to what are called semi-gray analysis. So a semi-gray analysis is one where we'll split the wavelength, the spectrum, up into little wavelength bands. And then within each wavelength band, we will require that each surface has a constant emissivity, but the emissivity can be different in different wavelength bands, and so that lets us at least start to look at surfaces that have spectrally varying emissivity. So surfaces like this one, we can't simulate it exactly, but we can simulate it more and more closely by breaking up the wavelength band into smaller and smaller bands, right? So that's a semi-gray analysis. If I want to simulate a surface that has a directional emissivity, then I'm more or less stuck with actually doing a full-blown Monte Carlo simulation where I'm, firing off rays and keeping track of what direction they go, and from that being able to put in probability distributions that reflect these kind of directionally dependent surface properties, right? But we won't get to that in this class. That's more of a 700 level radiation class thing, I think. All right, so what we'll do next time is learn how to deal with these kind of surfaces, so diffuse gray surface problems, and then once we've got that more or less figured out, it's a relatively easy thing to extend that process to a semi-gray surface analysis.